Okay, let's talk a little bit about pneumatic power. I'm going to be talking probably a little faster than you can write. Make sure you go to whatever guided notes I left you for what specifically you guys need to write down. That changes year to year. So make sure you guys look through that document for what you're looking out for and what you need to write. Of course, please make sure to pause wherever you need to. Okay, when we say pneumatics, we are talking about the use of a gas flowing under pressure, and it's usually really just air, and it transmits power to one location to another. Gas in a pneumatic system behaves a lot like a spring. Remember, air is compressible, right? Grab a balloon, we fill it with air, we squeeze it, we can compress that air, and we can use that to our advantage a little bit. Pneumatic systems use compressible gas, like we just said. They're kind of a quick, jumpier motion. They're usually not as precise. They require lubricant, are generally cleaner, and they usually operate around 100 pounds per square inch or 100 psi. And they usually use a little bit less power, not as powerful as hydraulics, which we'll get into later. Some early pneumatics uses, you may or may not know what this is. This is called a bellows, like a tool that a blacksmith might use, or even just to help stoke a fire. That's basically what a bellows was. There was this kind of rubber gasket material, and we'd move these two pieces of wood back and forth that were connected with this rubber. It let air in, it pushed air out through this nozzle. Really simple pneumatic device. Another one was actually America's first subway. This is really interesting. In New York City, of course, New York City has lots of subways, but this one was only 300 feet long. And look when it opened and look when it closed. It didn't last very long, but just forcing air through a tube and moving this little car that had people inside of it. When we think of pneumatics today, we think of robotic arms usually use, imagine like your fingertips have little suction cups, and that suction comes from pneumatics. So we can use robotic arms to squeeze things, to move things, to suck things, to grab them, to move them, to do all kinds of things. From cars to IV bags that we see in a hospital. Are used with robotic arms and use a lot of pneumatics. Whenever I say the word cylinder that we're going to be talking about, I'm talking about this type of cylinder, a cylinder that we might see to put on a label, on a hat, press a label onto something, press a part on something, and basically we have air that goes in here, and then it pushes this rod out. So when I say cylinder, this is what I'm talking about. Another use of pneumatics are, you may have been to the bank and seen the little bank teller machines, a great example. So we are pushing air through this tube, and that's where our check or our money or our deposit slip goes. All right, properties of gases. Gases are affected by three things that we really care about: temperature, pressure, and volume. Capital T, lowercase p, capital V. Reminder, gases have no definite volume. Gases are highly compressible. Gases are lighter than liquids. Okay, one concept that's very important is this idea of absolute pressure. Absolute pressure and gauge pressure. So gauge pressure is the pressure on a gauge. So I have my air compressor in my garage, and it says 100 psi. But that does not account for atmospheric pressure on all sides of the system. If we were at sea level, there would be about 14, go to this next slide, there would be about 14 pounds of pressure. So that just has to do with the atmosphere above us. If I run up to the top of Mount Everest, I'm going to have a lot less atmospheric pressure pushing on my head versus when I run back down to sea level, I have more of it pushing on my head. So absolute pressure, back up here. Absolute pressure is just atmospheric pressure plus our gauge pressure. Our gauge pressure might be 100, our atmospheric pressure is 14, and then we add those two together for our absolute pressure. Let's do an example real quick. Pressure is measured in pounds per square inch. We can write that as LB, which is pound, divided by inches squared, pounds per square inch, or we can just write PSI. So standard atmospheric pressure is 14.7 PSI. If a gauge reads 120, what is the absolute pressure? We just add 14.7 to 120 to get 134.7 psi. Absolute pressure, really simple. The next thing we need to talk about is absolute temperature. So 0 degrees Fahrenheit does not represent a true 0 degrees like absolute zero. Absolute zero, where there's no molecular movement, that's negative 460 degrees Fahrenheit. So absolute temperature is measured in, we use this special scale called Rankine, or degrees, capital R, degrees Rankine. So all we do is add 460 to Fahrenheit to get degrees Rankine. We can't have a negative temperature because you could then end up with a negative number. So if the temperature in the air in a system is 65 degrees, what is the absolute temperature? So our answer is 65 plus 460 equals 525 degrees Rankine. So that's why we use that degrees Rankine scale, and that's how we find absolute temperature. We just add 460 to degrees Fahrenheit. This will come in a little bit later. All right, we are almost done. We're going to do a Pascal's law example, and then we are done with this part. Pascal's law says pressure is exerted by a confined fluid acts undiminished equally in all directions. Pressure equals the force per unit area exerted by a fluid against a surface. A good example would be, imagine if you have swam into the deep end of the pool, you very quickly start to feel that pressure, and that pressure are these sinus cavities that you have kind of behind your cheekbones. And we feel that pressure from everywhere. It's not like we just feel the pressure from the top or just from the sides or just from the bottom. So if we understand that and read this definition again, pressure exerted by a confined fluid like our swimming pool acts undiminished equally in all directions. That's why we feel that pressure everywhere in our head. Okay, we need to know a couple things. Here's our symbol P for pressure, and that's pounds per square inch. We need to know our unit. F is force, and that's pounds, or lb. Area, A, capital A, and square inches. Okay, let's do a little example here. How much pressure can be produced with a 3-inch diameter cylinder and 50 pounds of force? Okay, so let's look at our picture. We have the diameter of the cylinder is 3 inches. We're going to apply this force of 50 pounds. Area is equal to pi r squared. So if we substitute, our radius, of course, is half the diameter. So that's where we get 1.5 from. Square 1.5, and we get 7.1 square inches. So we need to know our area. That's 7 square inches. Our equation equals pressure equals force over area. Our force is given. We just found our area. We're just about done. 50 divided by 7.1, we get 7 pounds per square inch, or 7.1 psi. So there's our first little law called Pascal's law. We learned a little bit about pressure, temperature, and area. We talked about absolute temperature. We talked about absolute pressure. We talked about some examples. We are good to go.